So let me know if my slide is visible.
Yes, ma'am.
So we shall be covering the topics from the chapter number 5 of, you already know about the book, Open Channel Flow by Muhammad Hanif Chaudhry. And the topics are as flashed. So it is a really very important topic while if as far as this civil engineering course is concerned. So and in this chapter you'll be able to uh, determine the relationship between the uh, uh, the distance and the depth of the flows in the river channel, and you'll be able to form the water surface profile using different equations and computations. So, in in real life projects, channel cross sections and bottom slopes are not constant with distance in natural channels, and these are varied in constructed channels to suit the existing topographical conditions for economic reasons. In addition, hydraulic structures are provided for flow control. These changes in the channel geometry produce non-uniform flows while changing one uniform flow condition to another uniform flow condition. Such flows are called gradually varied flows. If the rate of this variation of depth with respect to distance is small, the flow would be termed as rapidly varied flow. So you must understand the difference between the gradually varied flow and the rapidly varied flow, which are the classification of most important classification while studying the reverse flow analysis. Since the analysis of gradually varied flows is usually done for long channels, the friction losses due to boundary shear have to be included. These losses, however, may be neglected in the analysis of rapidly varied flows because the distances involved are short. So another most important parameter are the frictional losses, which have to be uh, uh, calculated when you are doing any analysis. May it be the pipe flow analysis or it is river flow analysis. So, and these losses are actually due to the friction originating from the boundary in any cross section. So when this the when so this friction losses are actually proportional to the distance uh, of the reach or distance of the channel, or distance if you are considering pipe, then it is proportional to the distance length of the pipe. But for rapidly varied flow, these shear stresses or these frictional losses can be neglected as the length in which that variation of depth is occurring is very small. So you can neglect those losses, those frictional losses, which are depending upon the distance. That is why those frictional losses would have very negligible effect, though there would be minor losses while you study the rapidly varied flow. So we'll be discussing further about this in detail in our uh, uh, in in a later time. In addition, the pressure distribution in gradually varied flow may be assumed hydrostatic because the streamlines are more or less straight and parallel. So first, let me know about hydrostat. What is hydrostatic law applied to the parallel streamlines? How do you define pressure? How can you say that pressure distribution in gradually varied flow may be assumed hydrostatic? What does that mean? Can anybody tell? So do you know about hydrostatic law? So if I ask you that apply that law in a fluid which is in stationary condition, when the fluid is contained in a vessel, how can you define that hydrostatic law applied to that scenario? Fluid is contained in a vessel, you can say. So how hydrostatic law can be applied to that fluid? So
Madam, the pressure, the hydrostatic pressure would increase with increase in the depth. P is equal to gamma H.
yeah, it's a part of this law. Hydrostatic law is actually, let me tell you, if I say that fluid is contained in a vessel and it is in stationary condition, so as the name implies, hydrostatic means uh, the law of hydrostatic would be, so if I consider 2 points inside this stationary fluid and I consider one datum line. So what about this? What about this distance? It is potential head. So I'll call it Z1. And what about this distance from the surface? It is pressure head at this point. So this is point 1 and this is point 2. So elevation head at this point is Z1 and pressure head at this point is, you can say, P1 over gamma. Is it pressure head? Do you know about that? I hope so. And at the second point, elevation head is Z2 and pressure head is P2 over gamma. So according to law of hydrostatic applied to the stationary fluid in a container, P1 over gamma plus Z1 is equal to P2 over gamma plus Z2. Okay, this is law of hydrostatic applied to the stationary fluid contained in a vessel. Okay, so the same law can be applied to the fluid which is in motion, but having the streamlines parallel, straight and parallel. Okay, so how can you apply that? You just if you introduce imaginary plane perpendicular to the flowing fluid, say, so if the fluid is flowing like this in a parallel streamlines, and you introduce uh, imagine, imaginary plane in between the flowing fluid. Okay, so uh, this is imaginary. So in this plane which is perpendicular to the parallel stream lines, this law is applicable. Like, you can say that the sum of pressure head, and if I take 2 points on this imaginary plane perpendicular to these parallel streamlines, 1 and 2, then I can say that P1 over gamma plus C1 is equal to P2 over gamma plus C2. So this is how you can apply law of hydrostatic to the fluid which is in motion. Okay. So in this case, this is one of the assumptions to compute the water surface profiles in gradually varied flow. Okay, which is this, that pressure distribution in gradually varied flow is assumed to be hydrostatic. It means that you are assuming parallel streamlines in the gradually varied flow. However, this is not the case in rapidly varied flow, where significant acceleration, uh, where there is significant acceleration normal to the flow direction, and that produce sharp curvatures in the streamline. So this law cannot be applied where you you come across sharp curvature in a streamline. Okay. So let's check further some uh, definition of uh, gradually varied flow and rapidly varied flow, and further classification of flow. Just check. You already know that for uniform flow through open channel, dy by dl is equal to 0. What does that mean? That change in depth with respect to distance is 0. Change in depth with respect to length of the channel is 0. However, for non-uniform flow, the gravity force and frictional resistance are not in balance. Thus, dy by dl is not equal to 0, which results in non-uniform flow. Okay, so it means that for you can say when the parameters of flow, which is essentially dy in case of open channel, which essentially depth is not changing with respect to distance, then you can say the flow is uniform, and when it is changing with respect to distance, then you can say that it is non-uniform. So there are further two classifications of non-uniform flow. One is called as gradually varied flow and the other is called rapidly varied flow. So you just check this channel, open channel, and you can distinguish between the rapidly varied flow and gradually varied flow. But you have to remember the definition that when the changing condition extends over a long distance, so this would be called as gradually varied flow. And in rapidly varied flow, change may occur over very abruptly, and the transition is in the confined short distance. So that is called rapidly varied flow. Okay, let's move to the assumptions of the governing equation, which we shall be using to compute the water surface profile. Actually, you will be making the water surface profile. Do you know about water surface profile? What is it? In that profile, you just show the relationship between distance and the depth. Okay, so and for gradually varied flow, you have to use some governing equation so that you will be able to know that whether the depth will increase with increase in distance or it will decrease with increase in distance. So what is that equation we are about to discuss? But before going to the derivation of that governing equation, just check the assumption. According to the assumption, the slope of the channel bottom is small. The channel is prismatic channel and there is no lateral inflow or outflow from the channel. So the channel is prismatic, it means the cross section is not changing. And there is no lateral inflow or outflow from the channel. It means that flow would be considered as steady. The pressure distribution is hydrostatic at the channel section. So the same law of hydrostatic would apply here also. And this is actually the assumption. The pressure distribution is hydrostatic at the channel section. Then the fourth assumption is the head losses in gradually varied flow may be determined by using the equations of head losses in uniform flow. So uniform, do you know any empirical equation which can be used to find out the depth, a uniform flow depth? I think you already have studied that.
Manning's equation.
Yeah, Manning's equation and Chezy's equation. So
yes.
you might have studied these two equations to determine the uniform flow depth. So we'll be using those equations to get the uniform flow depth. Okay, so it means that we won't be taking the whole reach of the river. So the whole reach of the river would be classified into sub-reaches in which we can assume the flow as, you can say, we can apply the uniform flow equations as the rate of change of depth to distance is very, very small in that small reach. So we'll be applying those uniform flow equations to find out the uniform flow depth in that reach. Okay, so let's check the derivation. Give me 1 minute, I'm just coming back. Okay, so we are going to derive the governing equation. So just check the first equation. You already know about that. It is actually the energy equation. Just check it. Check the figure, please. This is datum. This is channel bottom. And what about this? This is the water surface. Okay. And this dash line is actually the energy grade line. Okay. So this is H is actually the total head at one section. So H total head at this section would be equal to Z plus Y plus alpha into V square over 2G, where alpha is the energy coefficient, which is used to cater the difference between mean velocity head in a channel section and the velocity head. Okay, so computed with the mean velocity. So this alpha kate is that. I hope you all know about that. So we include all these heads to find out the total head. Total head would be equal to z plus y plus alpha v square over 2g. Practically, the alpha value has been is taken as 1. It can be it changes from 1 to 1.15 or 1 to 1.2, but practically it is usually taken as 1. So the next step is differentiating this equation with respect to x, differentiating with respect to x. So just check this equation, dh over dx, then it becomes dz over dx, dy over dx, and then differentiating this v square over 2g, first writing this v square over 2g in terms of this charge. When you write v square over 2g in terms of this charge, it will become q square over 2ga square. So as q is constant, q is considered as constant, and this 2g is also constant, alpha coefficient is also constant, so it will be coming out of the derivative term, and inside with it, inside the differentiation it will be area. Area is variable. So by giving the values or giving the symbols to dh over dx, dz over dx, and dy over dx, let's see what how this equation is transformed. So first, dh over dx is called as SF. SF is actually the slope of the energy line. Okay, so minus sign indicates that this negative slope. So that is why here you introduce minus sign. dz over dx is the bed slope. So this minus sign indicates that it is also the negative slope. Okay, the slope is negative. That is why, as with increase in distance, this potential head decreases. That is why you have to give negative sign over here. Okay, then this parameter is being the derivative of this 1 over a square is being done over here. You can just check it. So it is the derivative of area. So this derivative will be, okay, let me do it here. D over dx into 1 over a square. So if you take derivative, you'll first write like this. Like you will be taking derivative with respect to a. Okay. 1 over a square, and then dA over dx. So you'll be writing like this first. Then taking the derivative of this term with respect to dA, you'll get minus 2 over a cube. Okay. So this is this term, and then dA over dx. So again, you'll write this dA as b into dy. B is the width of the channel, and dy is the change in depth. So minus 2 into b into dy over a cube dx. So that's how you get the derivative. The same is written over here. Okay, so as dA is equal to b into dy. Okay, so putting, so if this is equation 1, 2, putting 2, 3, and 4 in equation 1, so what you'll get actually the governing equation. Let's see. So this you'll get this equation by putting 2, 3, and 4 in equation 1. So this is dy by dx is equal to s naught minus sf over 1 minus and this term. So this term bq square over gaq is actually a Froude number square, fr square. So according to the definition of Froude number, fr, you know that fr, and Froude number is the ratio of inertial forces to gravitational forces. You already know that. And we use this criteria to classify the flow into subcritical, supercritical, and critical flow. So Froude number, the formula for Froude number, you already know that it is V over under root gy. So fr square would be V square over gy. B square in terms of Q is Q square over A square. Gy. Okay. So by multiplying B and dividing by B, okay, now B into Y is actually area. So you can write that BQ square over AQG. Okay, so this is BQ square over, and if alpha is there, so you will be introducing alpha also here. So alpha BQ square over AQG. So this is how you can convert this term, which is this term, into FR square. Okay, and the final governing equation we get is this: dy by dx is equal to s naught minus sf over 1 minus fr square. So this is a very simple equation. So through this equation, you'll be sketching the water surface profile in gradually where it flows. Okay. So there is another method through which you can get this governing equation. Let's check that method also. So you know that total head is equal to z plus y plus y plus v square over 2g. So differentiating total head with respect to distance in horizontal direction. So same step has been uh, uh, taken here also. And then writing this v1 as the q square and y square. Okay, so this is discharge per unit distance, per unit length. Okay, so this is in terms of as q is equal to vy, small q is equal to v into y. Small q is equal to v multiplied by depth. Okay. So V can be written as uh, V can be written as Q over Y. So that is why they have substituted that V in terms of small q over Y. Then differentiating, after differentiation, they get the same value. Here dH over dx is SF, okay, is equal to minus S naught plus dy by dx 1 minus root number square. So this q square over gy cube is actually f square, root number square, okay. And the final form of the equation is the same. So you can derive, if in exam you are asked to derive the expression for uh, to derive the governing equation for water surface profile sketch, then you you can do in you can derive in both the from both the methods. Okay. So if dy by dx is positive, the depth of flow increases in the direction of flow and vice versa. So you need to calculate this term in order to get dy by dx, or you need to know the sign of this dy by dx so that you can sketch the surface profile. So the next topic is water surface profile classification. But before going further and uh, see the terminologies which are included in the classification of water surface profile, uh, we divide this whole depth of the channel into three zones to classify the flow, and we call the topmost this line above is zone 1, and then zone 2, and then zone 3. So for one steady flow, if you are given one discharge value, like Q is given, and that is constant for any channel, if we assume that, then you have one value for critical depth and one value for uniform depth. If you have this flow value with you, then you can calculate YC and Y naught. Okay, provided you are given with the cross-section values, uh, but you can calculate these two values. That is, Y naught is the YC is the critical flow depth, and Y naught is the uniform flow depth. So sometimes this YC is greater than Y naught, and sometimes it is less than Y naught. So uh, using the knowledge of the depths, you would be able to draw these lines, and if YC is less than Y naught, then this distance would be, if I'm saying that YC is less than Y naught, then this distance would be YC. Okay, so this first zone would be in the you can say in depth YC. The second zone would be here, from here to here, or you can say from here to here, it is Y naught. Okay, so this is the scenario when Y naught is greater than Y, and the zone which is above this line would be called as zone 1. So using the magnitudes of these depths, you'll be dividing the depths of the depth of flow into 3 zones: zone 1, zone 2, zone 3. Okay, so this is when y naught is greater than yc. Okay, so there is another scenario in which y naught is less than yc. So in that case, this zone would be from here to here, it would be y naught, and from here to here, it would be yc. Okay, and the zone and above above this line, that would be called as zone 1. Above the line of critical depth line, that will be called as zone 1. So depending upon these zone classification, you will be classifying the water surface profile also. Okay, let's check the text written in this slide. Zone 1, space above the topmost line. When y is there can be 2 scenarios for space above the topmost line. When y is greater than, when the depth of flow is greater than the uniform flow depth, and which is greater than yc. So this is the case 1. Okay, and when y is greater than yc and it is greater than y naught. So zone 1, when the depth of flow is here, okay, for some discharge value, when the depth of flow is at this point, at zone 1, okay, so y is the depth of flow, and y naught and yc can be calculated for the discharge value, for the given discharge value. And zone 2, space between top line and the next lower line. So this is zone 2, and there can be 2 scenarios in the zone 2. One is this, which is y naught greater than yc, okay, and in between there would be y. So y lies here in this zone, okay, and when yc greater than y naught, and in between yc and y naught there would be y. So this is zone 2. And zone 3, space between the second line and the bed. Okay, and there would also be 2 scenarios for that. Okay, in one case y naught is greater than yc, and in the other case y naught is less than yc. So there are 3 zones, and using these zones you'll be classifying the type of water surface. Okay. So before discussing the type of water surface profile, you know already that what is subcritical flow and what is the criteria for subcritical flow, critical flow, and supercritical flow. So in subcritical flow, when the bed slope is less than SC, SC is the critical slope which can be calculated using uh, uh, using the uh, using the formula and using the discharge which is given. So when S naught is less than SC, then Y is greater than YC. So that kind of flow is called as subcritical flow, and in that case Froude number is less than 1. So when S naught is equal to SC, so there is some critical slope value for some specific flow. So if S naught, the value of bed slope, is equal to that critical value of slope, and Y is equal to YC, then flow would be termed as critical flow, and in that scenario, the Froude number value would be 1. So when S naught is greater than SC and Y is less than YC, that scenario is supercritical flow, and Froude number would be greater than 1. So you already know about the types of flow. Let's check the types of water surface profile and the types of bed slopes. Okay, when would we call the slope of bed as mild? When this y naught value is greater than yc and s naught is less than sc. So the slope, bed slope, would be called as mild slope. Okay, like in this case, uh, here the s naught is less than the critical value of slope, and also y naught is greater than the critical depth. Uniform flow depth is greater than critical depth. Then in that case, the slope, the bed slope, can be classified as mild slope. Then the criteria for critical slope is y naught is equal to yc, s naught is equal to sc. Steep slope is when y naught is less than yc and s naught is greater than sc. Adverse slope is when s naught is negative, and horizontal slope is when s naught is 0. So these are the criteria which are used to classify the bed slopes of the river channel or river reach. Classification of surface profiles, just check it. So in all the 5 types of bed slopes, you'll be having almost in every type except horizontal and uh, adverse and critical view, you'll be having 3 classification of water surface profile. And let's check the mild slope. Type 1, if the stream surface lies above both normal and critical depth of the flow. Okay, when the depth of flow is in zone 1, then you can say that it is, and this criteria is fulfilling, like it is mild slope and depth of flow is in zone 1, so that would be called as M1 profile. Okay, and when the same criteria but the depth of flow is between y naught and yc, then it would be called as M2, and the same criteria with depth of flow in zone 3, then it would be M3. Okay, so you will be associating those 3 zones with one bed slope. Okay, so similarly, steep slope would be a steep classification of surface profile can be S1, S2, S3, and you know how can you classify that accordingly. When depth of flow is in zone 1 and this criteria is fulfilled, this one, y naught is less than yc and s naught is greater than sc, then you can say that it is S1. And when depth of flow is in zone 2 and this criteria is fulfilled, then the classification is S2. Okay, and when depth of flow is in zone 3 and this is the bed slope classification, steep bed slope, then it would be called as S3. Okay, so in the next slide, we'll be determining whether how can you determine the this value of dy by dx as negative or positive. So you already know that when dy by dx is negative, it means the depth of flow is decreasing with increase in distance, and positive, the depth of flow is increasing with increase in distance. So how can you determine the negativity and positivity of that slope? That is very important to sketch the water surface profiles. So let's check for wide rectangular channel. In case of wide rectangular channel, this hydraulic radius can be taken equal to y, because if you remember the definition of hydraulic radius, it is area over perimeter. Okay, so for rectangular channel, area is by and perimeter is what, b plus 2y. Okay, so when this perimeter will nearly be equal to b, as this 2y value is very negligible as compared to this b value. So you can simply write like this: by over b, by neglecting this 2y term, as it is very lower value than b. So this b and b cancel, so hydraulic radius can nearly be said as y. Okay, for wide rectangular channel. So when hydraulic radius is equal to y, then you can just transform the Manning's equation. This is Manning's equation. So instead of writing r here, you write y here. Okay, for wide rectangular channels. So this is Manning's equation, which is steady state resistance law, and you use this equation to find out uniform flow depth. Then converting this equation in terms of small q, as you know that q is equal to small q is equal to v multiplied by y. So putting that and v would be equal to q over y. So writing this whole equation in terms of small q. So s can be determined. So here we assume that the slope of the energy line is equal to the bed slope, or you can say the energy line is parallel to the bed slope. This is the assumption over here. So for the case of steady flow in a small reach, you can safely assume that the slope of energy line and bed slope is constant. So S is equal to n square q square over y raised to power 10, and power is 10 by 3, and S naught can be written like this. S naught is the uniform flow in rectangular channel. So S naught can be written like this: n square q square, same equation but with y naught. Y naught is the uniform flow depth. Okay, and y is the flow. Okay, so using these two equations, just get the ratio of S over S naught, you'll get this, Y naught over Y. So our aim is to define the, you can say, numerator of this governing equation. We have the governing equation with us, and we have to find out whether dy by dx is positive or whether it is negative. In order to get that, we will have to know the sign of the numerator and the sign of the denominator. So to get the sign of the numerator, you'll be using this equation, S over S naught. So when y is greater than y naught, what about S and S naught? S would be less than S naught. So it would be reciprocal. When y is greater than y naught, S would be less than S naught. Okay, so and the numerator would be positive. So you have to check the values of y naught and y. Okay. So when this y is greater, it means that S is less than S naught, and when S is less than S naught, the numerator would be positive. Similarly, when y naught is greater than, then S would be greater than S naught. Okay, so in that case, when s is greater than s naught, the numerator would be negative. Okay, so in order to get the sign of the denominator, you have to investigate the Froude number. Okay, for Froude number, you'll just check the value of y naught and whether the depth is greater than yc or it is less than yc. Okay, when the depth of flow is greater than yc, this Froude number would be greater or less than 1. When depth is greater than critical depth value, which kind of flow is that? Subcritical flow.
Sub.
Okay. So for subcritical flow, what about the denominator value?
Less than 1, ma'am, which means positive.
Which means positive. Very good. So for subcritical flow, Froude number would be less than 1, and this value would be positive, and vice versa for supercritical flow. Okay, so this is how you'll get the sign of dy by dx. Let's check further the what surface profile types. So for mild slope, when the bed slope is mild, it means that y naught is greater than yc and s naught is greater than, sorry, s naught is less than sc. So this is mild slope. Okay, just remember the criteria of mild slope. So when in mild slope, water surface profiles are classified into 3 types: M1, M2, and M3. So what about M1? When the depth of flow is in zone 1, then you can call that profile as M1 profile. Okay, that is when y depth of flow is greater than y naught and it is greater than yc. So the profile would be called as M1. So if this is the line in this figure, if this line is critical depth line, yc, this is y naught. Okay, and M1 profile means that y is greater than, like this value here, y is greater than y naught. And if y is greater than y naught, then it means that it is in zone 1. Okay, so zone 1 profile is M1 profile. Okay, let's check the sign of dy by dx in that. S naught minus s. So in that case, why it is positive? Because you have to check the value of y and y naught. If y is greater than y naught, then what about s and s naught? Just check the equation again, this equation. When y naught is less than y, then you can say that s would be less than s naught, isn't it? When y naught is less than y, then is less than s naught. So apply this equation here, then you can know the sign of numerator. So y naught is less than y. So s is less than s naught. It means that numerator is positive. And what about the denominator? Froude number for subcritical flow would be less than 1. So denominator would be positive also. Here we have to fn square. It is not fn. So there is mistake here. So just check the Uh, Next figure like this. In this figure, you can say that the depth of flow, which is y, it is in between the y naught and yc. So it is in zone 2. So these are the depths in this gradually varied flow. Okay, if the depth of flow varies between y naught and yc, so it means that it is in zone 2. Okay, so and just check the signs of numerator and denominator using the criteria. So in case of M2 profile, y naught is greater than y, as it is in between y naught and yc. Y is in between y naught and yc. So y naught is greater than y and it is greater than yc. So the numerator can be written as y is greater than y naught. So S would be greater than S naught, as y is greater than y naught. This is the formula. Just check this. Or you can say y naught is greater than y. Y naught is greater than y. So S would be greater than S naught. So if S is greater than S naught, then numerator will be negative. Okay, and similarly, as the flow is subcritical here also, so denominator is positive, as Prout number would be less than 1. So negative, so you can just classify the M2 profile as negative slope profile. So you can say that with increase in distance, the depth decreases in M2 profile, surface profile. Okay, so this is how you can sketch the water surface profile using the governing equation. Similarly, you can just sketch this the third, when the depth of flow is less than yc value, as this length, this depth is yc. So when the depth of flow is less than yc, so these are the points of depth, and it is considered as third zone. So when depth of flow is in the third zone, then you can say that it is M3 profile. Let me know if there is any question.
Excuse me, ma'am.
Yes.
Ma'am, to make it simple, can I say that on a mild slope, when the flow line is above the normal depth line, the dy by dx is positive, and the moment it starts to go down below the normal depth line and then below the critical depth, the dy by dx becomes the slope difference becomes negative and dy by dx becomes positive again. So, am I right? If I've been, may I repeat it?
So you are saying, yes, you are right. You can when theoretically you can, if you want to say that.
Qualitatively, yes.
Yeah, qualitatively you can say that you are right, but to further quantify your statement, you can use this governing equation also. Actually, this governing equation is the criteria to determine the depth of flow increasing or decreasing with increase in distance.
Indeed.
So yes, you can learn or you can memorize using this qualitative approach, but to conceptually you can use this governing equation to find out dy by dx, and that you would be using in a later time period uh, for the numerical problem. Okay, so this is how you can classify this M1, M2, M3 profile, and you can sketch that accordingly. Okay, let's check the water surface profile in steep slope, and the same criteria, same governing equation would be used to find out the distance versus depth slope Okay, so the gradient of water surface in case of steep slope would be positive when the depth lies in zone 1. Okay, so how it is positive, you can use the governing equation to get the positive slope. Okay, so in this case, what about S and S naught? In this case, whether S naught is greater than S or it is less than S.
Greater.
Greater than S. So that's why the numerator would be positive. So, and what about Froude number here, whether the flow is supercritical or subcritical? Subcritical. As the depth of flow would be greater than the critical value of depth, so we can classify that that Froude number is in subcritical range. So similarly, you can determine dy by dx for other criteria, or for zone 1, for zone 2 and zone 3. So when the depth of flow is in zone 2, then you can call that slope of water surface as S2. When the depth of flow is in zone 3, you can call that slope as S3. And how the slope varies, how can you sketch the water surface profile? You can use the governing equation to do that. The information you'll be needing after using the governing equation is whether it is declining or it is increasing, whether the depth is decreasing or it is increasing. Okay. I hope you understand. What's up for critical slopes? You can see that we have the criteria like depth of flow can be greater than y naught. As in critical slopes, y naught is equal to yc. That is, uniform flow depth would be equal to critical flow depth. So when the flow depth is greater than these two values, or when the flow depth is greater than yc, there can be two scenarios. One, flow depth greater than yc, and the other flow depth less than yc. Okay, so that is why we'll be having only two classifications for critical bed slope, C1 and C3. Okay, C3 would be when the depth of flow is in the zone 3. There can be zone 1 and zone 3 only. As zone 2 is merged. Why merged? Because y naught is equal to yc. Okay, and the same criteria would be used to determine the increase to determine the slope of the water surface profile. Okay. So when the water surface, when the bed slope is horizontal, what happens then? When bed slope is horizontal, the uniform flow depth comes out to be infinity. So in that case, we'll be having two zones only. One would be between the uniform flow depth and yc, and that would be called as zone 2, and the other would be less than yc. The depth of flow is when the depth of flow is less than yc. So there would be two zones. So so accordingly, we can classify the water surface profile as H2 and H3. Okay, so and the same criteria governing equation will be used in order to determine the slope of the water surface profile. So adverse slope in adverse slope, the uniform flow depth is infinity. So this depth, this uniform flow depth would always be greater than any flow depth practically occurring or critical depth. So that is why here also we'll be having two zones, 2 and 3, in between uniform flow and critical depth, and less than critical depth when the depth is less than critical depth. So adverse water surface profile slope, adverse slope, wet slope have two water surface profiles, A2 and A3. So this is the question. Let's check it. Classify the water surface profile for given data. Channel type rectangular. The value of Manning's roughness coefficient is given. N is equal to 0.013. B is equal to 1.6. S naught is given. Q is equal to 1.7. Y varies from 0.85. Q is equal to 1.7 meter cube per second. Okay. Y varies from 0.85 to 1 meter. So how to classify the water surface profile? You have the governing equation with you. So in that governing equation, you have you don't have the uniform flow depth value. So first you need to calculate the uniform flow depth value using the Manning's equation as you are given with the Manning's roughness coefficient. So you can use the Manning, you can find out the uniform flow depth using trial and error method, or you can just directly solve it in the calculator using equation solver. Okay, so Y naught came out to be 1.047 meter, and this Y naught value is greater than Y, as Y varies between 0.85 to 1. So let me know about the classification.
M2?
M2. How can you say that when you didn't calculate the
The
YC
Y's.
value? Yeah.
Yeah. For now,
YC value.
yes. For now, just a guess
Yeah.
that it is below the NDL line, so that's why.
Yeah. So you need to calculate Y naught as well as YC both to classify the water surface profile. So YC value can be calculated using the formula Q square over G raised to power 1 by 3. Okay, and you get that YC. So when now you can say with confidence that it is M2. So in exam, we'll be needing yes, we will be needing your qualitative analysis, but you just have to show some quantity so that you would be able to fulfill the criteria for that specific slope you are determining. Okay, so here Y naught is greater than Y and it is greater than YC, so the profile can be called as M2. And if I ask you about dy by dx, so here we have Y naught greater than, this is the conclusion, Y naught greater than Y and it is greater than YC, so that is why it is M2. And how it can be sketched?
Negative map. There will be a drop.
Yes, it would be negative. So using the equation, you can have the idea of that uh, uh, slope of water surface. Okay. So let's check the next question. Determine critical depth. Next question is this. Classify the water surface profile for given data. Rectangular channel, 0.013 is the Manning's roughness coefficient, B 1.6, S naught value is given, and you can see that it is minus 0.0004. It means that it is adverse. So which type of adverse slope is this, and how can we classify the water surface profile as there would be two types of adverse water surface profile. It is A2 and A3. Okay, so uh, uh, we will have to check that by calculating the value of YC, and they have given us the values of Y, which varies from 0.85 to 1 meter. So let's check what to calculate now. Uniform flow, we don't need to calculate uniform flow depth, as it would always be greater than the depth of flow, as it is. It will be infinity. So you need to calculate critical flow depth not to get the classification. So critical depth is calculated here. It is 0.486. It means that depth of flow is greater than critical depth value. Okay, this would be the result. Y naught is greater than Y, and it is greater than YC. So the classification of this flow would be A2. What surface profile is A2. Okay, so there are some other questions which I want you to do. Uh, so we may have a small break, fair break, 10 minutes, and we'll be uh, coming back at about 6:35. Okay, so then it's your assignment to do the classification of a surface profile. You'll be solving these three questions after the prayer break. Okay, thank you so much. Okay, students, please let me know if you have solved question number 1 in this slide. Classify water surface profile, uh, and the data is given. And they have also provided with the values of y, and they say that value of y varies from 2.5 to 3 feet. So you are given with Manning's roughness coefficient. So to get the uniform flow depth value, you'll be using Manning's formula, and you know about Manning's formula already. Let me write it for you so that you can uh, calculate the uniform flow depth value. So this is Manning's formula. Q is equal to 1 over n a raised to power 2 by 3 s naught 1 by formula to get the uniform flow depth. You have to do all these questions right now. So that's why this would be your assignment, and you'll be submitting this assignment after your class.
Excuse me, ma'am.
Yes.
Question one, a rectangular channel.
Yes, it is rectangular channel. Rectangular channel.
I have solved it assuming it as a rectangular channel.
Okay. Have you got the value of y naught?
Yes, ma'am.
So kindly do it, and do it like you have to present it as an assignment. So I'll be taking your assignment, and you'll be submitting it in MS Teams. Okay. So by uploading its picture.
Okay, ma'am.
So find the uniform flow depth, then uh, uh, critical depth, and the formula you'll be using would be this formula.
मैम ये सबमिट अभी होनी है?
हाँ जी, ये आप अभी कराएंगे, और मैं फिर डॉक्टर हमजा को ये सारी असाइनमेंट्स दे दूंगी।
ठीक है।
सिर्फ 3 क्वेश्चन हैं, ये आप जल्दी से, मेरे ख्याल में ज़्यादा देर नहीं लगेगी। जस्ट इसमें टाइम लगेगा कि यूनिफॉर्म फ्लो डेप्थ निकालने में थोड़ा टाइम लगेगा, लेकिन बाकी तो मेरे ख्याल में लंबी असाइनमेंट नहीं है। बेस्ड ऑन द क्राइटेरिया of the depth, so you'll be ये कॉपी करनी है। ओके, पहले क्वेश्चन में वाई नॉट किसी ने निकाला? वाई नॉट की वैल्यू किसने निकाली है?
यस मैम 3.17 है।
ओके, और वाई सी?
$1.65.
Yes, ma'am. 1.6.
Okay. So in this case, depth of flow is from 2.5 to 3 feet. It means that,
M2.
yeah. So depth varies between Y naught and YC. So you just let me know the classification. How can we classify? As you see that Y naught in
Ma'am,
this
we
case.
classify it as a mild slope.
Yeah, in
Excuse
mild
me, ma'am.
flow, Y naught is greater than YC.
Excuse me, ma'am.
Yes.
And there is an issue with the Manning's equation because we have been taught that if you're going through the SI unit, the formula is 1 by n. If it's FPS system, then it is 1.49 divided by
Yes,
n.
yes, you are right. When it is in the British gravitational system, yes, you'll be using this 1.49. You are right. So have you used this formula or this one? Have you used this coefficient for the conversion or not? To find out this, why not?
जी मैम ये यूज किया
Yes, ma'am.
Okay. As y naught is greater than yc, it means that sc is greater than s naught. And this is actually the criteria for mild slope. Just remember that. As y naught is greater than yc, it means that sc is greater than s naught, or you can say s naught is less than sc. Sc is the critical slope value. Okay, just do the this question and find out y naught and yc, and then classify the water surface profile. Just please write down the given parameters, and you can do it after the class, or when I'll be finishing the topics I have to cover today. Okay, so just write down the given parameters for both of these questions, and this would be considered as your assignment number. Which assignment it would be?
मैम
Have you
सेकंड
submitted? Okay, assignment number 2. Okay. So these only 3 questions in the assignment, and you'll be giving, or you'll be submitting in MS Teams. Write the given parameters, please. और ये काम आज ही मुझे चाहिए, not later than today. मैं ये जो स्लाइड्स हैं ये अपलोड कर दूंगी आफ्टर द क्लास, तो आप इसको देखते हुए आप कर सकते हैं अपना काम. Okay, let's check the next slide. Okay, this is another question. Please check it. The flow in 15-foot wide rectangular channel has a constant bottom slope is 1400 cusecs. A computation using Manning's equation indicates that normal depth is 6 feet. At certain section, the depth of flow in the channel is 2.8 feet. Does the depth increase, decrease, or remain the same as one proceeds downstream from this section? Sketch the physical situation where this type of flow will occur. So writing, the first step is to write the given parameters. We have been provided with width of the channel, discharge, and then uniform flow depth is also given to us. Then they have given us the uh, one depth value, and they we have to determine that whether uh, the downstream of this depth value uh, the the slope increase, decrease, or it remains same. Okay. So how can you do that? Yes, before deciding about the water surface profile, you have to find out critical depth value. You have the value of uniform depth with you, and then seeing the critical depth value, you can decide the classification of flow. So as YC is 6.47, which is greater than the uniform flow depth, and which is 6 feet, and it is uniform flow depth is greater than the depth given in the question. So it means that it is as YC is greater than Y naught, it means that it is the bed slope is steep, and in steep bed slope, which profile would be that? You'll be deciding about the profile using the depth of flow value, which is 2.8. So 2.8 is less than YC and Y naught. So it is in depth of flow is in third zone. Okay, so the profile would be termed as H3. And how would you determine uh, the profile, or you can say gradient of water surface profile, using the governing equation and the numerator and denominator? So when Y naught is greater than Y, when Y naught is greater than Y, what about S naught and S? ये सही लिखा हुआ है यहाँ पे? When Y naught is greater than Y, S naught and S would be greater than S naught. So यहाँ पे ये गलती हुई हुई है, ये जरा चेक कर लें, इसको रेक्टिफाई कर दीजिए. Am I audible?
Yes, you are.
Okay, तो ये देख लें, ये न्यूमरेटर में ये पॉजिटिव लिखा हुआ है. ठीक है, तो यहाँ पे नेगेटिव आएगा. इसी तरह फ्रूट नंबर जो है, it would be greater than 1 as the flow is supercritical, depth value is less than YC. So denominator would also be negative. So negative, फिर वो positive बन जाएगा. That would be the reason for the positive gradient of the water surface profile. Okay? तो ये जरा रेक्टिफाई करना है आपने. ये नेगेटिव है. Okay, how can you draw some physical situation for this case, for this type of case, the S3? So where would be the control section? Would it be downstream of the
Upstream, ma'am, a sluice gate.
So it would be upstream.
Yeah.
So as the flow is supercritical in this case, so the control section should be made upstream of this scenario. Okay, so अगली स्लाइड में ये बना हुआ है, ये जरा चेक करें. तो कई दफ़ा क्वेश्चन आपको एग्जाम में इस तरह का भी आ सकता है that you have to sketch the physical situation where this type of flow will occur. तो ये आप फिर अपने ध्यान में रखना कि कौन सी सिचुएशन ऐसी हो सकती है. Whether you have to check or think whether you will be making the control section. What is the control section? Can anybody define control section? So what is the control section in this case?
Ma'am, it controls the ratio between depth and discharge. So
Yes.
at this point, you get a critical flow for maximum discharge.
Yeah, you can say that. You can say so. Control section is actually where there is a, you can say there is a change in parameters of flow, or you can say that when the depth changes due to that particular section. Control section can be any sluice gate, change in the bed slopes. Okay, so where there is a change in the bed slope, that section would also called as control section. When there is any obstruction in between the flow and there is a change in the parameters of flow like depth and velocity changes, then it means that there was a section somewhere upstream or somewhere downstream. So when you are observing the gradually varied flow, then there is some control section either upstream or downstream. So when the water surface profile has some gradient, it means there is some control section upstream and downstream of that profile. Okay, so this can be the physical situation where you can come across this kind of water surface profile after the sluice gate, downstream of the sluice gate, or you can say that S3 profile governs the upstream control section. Okay, so this is how you have to make the physical situation. Let's check the next question. A laboratory flume 10 inches wide and set on a slope given with measured flow of 0.1516 cusics. The depth is observed to be vary between 0.36 to 0.366. Classify the water surface profile as one forms of 10.20 for the previous question. Show all necessary calculations and sketch the profile. तो ये भी बिल्कुल सिमिलर क्वेश्चन है. इसमें भी आपको width of the channel दी हुई है, डिस्चार्ज की वैल्यू दी हुई है, बेड स्लोप दी हुई है. So you'll be using Manning's equation to get the uniform flow depth, and then you'll be determining critical depth value using uniform flow depth and critical depth value. You'll be classifying the flow, classifying the water surface profile. So according to the values in this slide for critical and uniform, the slope is M1. And you also see that the depth is observed to vary from lower value to higher value. It means that it is positive slope. So, and you can draw the profile like this. And M1 profile is actually the gradient of M1 profile is positive. Okay. And yes, you can also use the criteria for M1 profile, that is y is greater than y0 and it is greater than yc. So these are the kind of questions you can expect in the examination. Again, similar kind of question. I expect that you'll do it yourself. You need to do the practice of calculating the uniform flow depth correctly and the critical flow depth correctly, so that your answer of classification is correct. Okay. Okay, just check this figure. This is the demonstration of hydraulic fluid line and energy line, and when the flow is ideal, this energy line would be truly horizontal. And when you say that there would be some head losses, then this energy line will be like this. It would be slanting. Okay, so the energy equation can be written for open channel flow would be like this: Z1 plus Y1 plus V1 square over 2G is equal to Z2 plus Y2 plus V2 square over 2G plus HL. When we consider two sections in the flow in the reach, okay, and delta L is the length between these two sections, okay. So So if we, there are some questions in which you'll be calculating the length between the two depths. The depth of the water surface is given, would be given, and you would have to calculate the distance between the two depths. So to do that, you should have one. You'll be doing like this. Though we will be discussing this equation in the next class also, but for the time being, to do the next question, which in which this formula will be applied. Uh, so, uh, how how can we get this formula, this change, this delta L between the two sections? Just check that. So slope of the energy line is actually head loss per unit change in length. So just check that. Head loss over delta L would be called as the slope of this energy line. Okay. Though gradient is actually the tangent theta, but here uh, we are taking the sine theta. Okay, so uh, in this case, slope of the energy line is delta z over distance. Okay, sorry, delta x, delta z divided by delta x is the bed slope, sorry, and it can be, and the slope of energy line is head loss per unit length. Okay, what is the let me know that why you when the angle of bed slope is very small, when the angle theta is very small, then you can safely imagine that tangent theta is equal to sine theta for small angles. So that is why this is sine theta. The delta z over delta L is sine theta, and uh, this is tangent theta, delta z over delta x. So in this case, theta value is less than 6 degrees. So you can safely assume that sine theta is equal to tangent theta. Putting these two values in equation 1, you'll get this formula. Okay, E1 and E1 and E2 are the energies, Y1 plus V1 square over 2G, and Y2 plus V2 square over 2G, and the rest is has been substituted from this equation. So finally you get this equation for delta L. Delta L is equal to change in change in energy divided by S minus S naught. Okay. So any question regarding this these steps, please let me know. An approximate analysis of gradually varied non-uniform flow can be achieved by considering a length of stream consisting of number of successive reaches in each of which uniform flow occurs. Greater accuracy results from smaller depth variation in each reach. So uh, when uh, when you have to evaluate this delta L value uh, uh, for larger difference of depth, then you have to use this formula by considering the smaller reaches in between those lengths. Let's check this question and then we'll know about that. A rectangular flume of plain timber is 1.5 meter wide and carries discharge of water. The bed slope is given, and at a certain section, the depth is 0.9 meter. Find the distance to the section where depth is 0.75 meter. Is the distance upstream or downstream? So you'll be calculating the distance to the section where depth is 0.75. Like uh, at one section, the depth is 0.9 meter, and at another section 0.75 meter. So you have to uh, calculate the length between the two sections. How can you do that? So for this much variation of length, we'll be doing just straightly, and we'll be calculating we'll be using this formula delta L is equal to E1 minus E2 over S minus S naught. E1 is the energy at section 1, which has the greater depth. E2 is the energy at section 2, which has the smaller depth. And the slope of the energy line can be calculated using the mean values of the velocities and hydraulic radius at both the sections. So calculating the areas, then perimeters, then hydraulic radius, then velocities using the formula, and then calculating mean of hydraulic radius and mean velocity, putting RM and VM in the slope formula, you'll get the slope of the energy line. Putting the putting the values in it, and then you'll see that delta L is coming out to be 317.73 meters. And upstream, why they have said that it is upstream? Actually, they are actually calculating the direction of flow. Is the distance upstream or downstream? So how can you know the direction of flow when this data is being given to you? Direction of flow. How can you get the direction of flow? And okay, if you are finding out the delta L value through this formula and it comes out to be positive, what does that mean? So it means that this energy at section 1 is greater than energy at section 2, and when the energy at section 1 is which is at the higher depth, section 1 is 0.9 and section 2 depth is 0.75. So the direction of flow from when it comes out to be positive, it means that direction of flow would be from higher energy level to lower energy level. Okay, so that is why you can find out the direction of flow, and it is said that it is upstream. This depth, this 0.75 depth is upstream. Or you can say that flow direction is from 0.9 meter to 0.75. Okay. So let's check some of the rules for sketching the water surface profile. Uh, any channel section at which there is a unique relationship between the flow depth and the discharge, that channel section, which your class fellow has already told us that the definition of control section, that channel section is referred to as control section. The properties of surface profile we discussed are for prismatic channel having control section either at upstream or at downstream end. In real life, however, a channel system may have several control sections. In addition, channel system having variable cross-section or bottom flow may be divided into several prismatic channels. So in order to use that governing equation and whatever equations we have studied, you just keep the assumptions in mind that you need to, if you are applying the uniform flow equation, then the channel should be prismatic, and you have to divide whole reach into small prismatic channel. If in the whole river reach there is change in the variable cross section or change in bottom slope. So at every reach you need to determine the water surface profile using the governing equation. If you are using that governing equation to find out the water surface profile. To qualitatively sketch the profiles in these cases, a number of guidelines are outlined. Divide the channel system into prismatic channels, and for specified discharge, roughness coefficient, and channel section, compute normal and critical depth in each channel. Now, using the exaggerated vertical scale, plot the channel bottom and the normal and critical depth lines. Then on this diagram, mark the locations of controls, that is the location where the water surface profile passes through critical depth, and identify the channel reaches where the flow is expected to be uniform. So you first this should be done. Like at any control section, the depth of flow will be equal to the depth of flow will pass through the critical depth line. Okay, and you have to also identify the channel reaches where flow is expected to be uniform. So a downstream control governs if the flow is subcritical, and an upstream control governs if the flow is supercritical. It is possible to have situations where part of a channel is governed by upstream control and part of the channel is governed by downstream control. So let's check the examples of some profiles in which you have to sketch the water surface profile. So just check this. This is control section here. In terms of dam, and just check, and the uniform flow depth is given and critical depth value is also given. So, and here when the flow is subcritical, you can see the control section is at downstream. Okay, and here when the profile, or you can say flow, is supercritical, in which zone 3, sorry, when the flow is supercritical, the control section is at the downstream side. Similar is the case here when in supercritical, in case of supercritical flow, sorry, in this case it is at the upstream. Okay, And this is also when the flow is subcritical, which is M2 profile, it is subcritical. So the flow is at upstream. But in case of supercritical flow, the control section is at मैं उल्टा बोल गई हूँ यहाँ पे ये डाउनस्ट्रीम है सॉरी प्रोफाइल के डाउनस्ट्रीम में कंट्रोल सेक्शन और सुपरक्रिटिकल फ्लो में अपस्ट्रीम में कंट्रोल सेक्शन ठीक है ये एक बात जरा याद रखने वाली है इसी तरह ये नीचे वाला आप चेक कर सकते हैं स्लूज स्केट है उससे पहले जो भी फ्लो है प्रोफाइल इज M1 और यहाँ पे भी अगेन यू कैन सी दैट द कंट्रोल सेक्शन एट downstream, okay, for subcritical flow, and for supercritical flow, control section is at upstream. Or whenever supercritical flow changes to subcritical flow, hydraulic jump is formed. Okay, whenever depth approaches to critical depth line from supercritical to subcritical. And then a lot of energy is being dissipated in the form of hydraulic jump. Okay, would you be able to draw or sketch the water surface profile in this case? आपके पास यूनिफॉर्म फ्लो डेप्थ की वैल्यू है और आपके पास YC की वैल्यू है कौन सी टाइप की प्रोफाइल होगी यहाँ पर के नीचे इसका सोल्यूशन भी दिया हुआ है कि आप चेक कर सकते हैं तो यहाँ पे just remember that control section is downstream so it would be subcritical flow and the profile would be when mild slope would be mild and depth of flow you can say that you can sketch like this. It can be like this. Okay. So M1 profile you'll be drawing, and at downstream of the sluice gate, so it is S3 profile. So please practice to sketch the water surface profile, and you can practice from chapter number 5. From the book of Open Channel Flow by Muhammad Munif Chaudhry. This is the question from that book, and there are other questions which have been taken from the book, which is called Fluid Mechanics with Engineering Applications by E. Jonathan Moore and Joseph B. Franzini. ये जो questions हैं जो पीछे हम कर रहे थे ये सारे questions उस book में से हैं ठीक है और ये जो क्वेश्चन है चैप्टर नंबर 5 में से मोहम्मद मुनीफ चौधरी की बुक में से so you can practice from that book. There are some other examples which I expect that you check those examples yourself or try to draw the water surface profile yourself and then check the solution. I hope you'll be able to sketch that as it has already been discussed in advanced open channel flow. कोई ऐसा स्टूडेंट है जिसने एडवांस ओपन चैनल फ्लो नहीं पढ़ा हो क्लास में कोई ऐसा है
Madam, Mr. Jamil and I was not class of open channel art.
अच्छा ठीक है तो आप इसको चेक करें कहीं भी आपको यानी हेल्प की ज़रूरत होगी तो आप पूछ सकते हैं ठीक है आप ईमेल कर सकते हैं यू कैन ऑलवेज ईमेल मी यू कैन सेंड मी थ्रू MS Teams ठीक है कोई भी मैसेज आप MS Teams के थ्रू मुझे दे सकते हैं लेकिन ये कि थोड़ी सी क्वेश्चन एटलीस्ट जो स्लाइड्स में है ना इनको थोड़ा करने की कोशिश करें कि कैसे हैं तो ये भी एक क्वेश्चन है जो कि मैंने मेरे ख्याल में ये मैंने इंटरनेट से लिया था, जिसमें वाटर सरफेस प्रोफाइल sketch हुई भी है already. Just uh, check it that how have they made it when the depth of flow or you are given with the uniform flow depth and critical depth value. So वो line अगर आपके पास है तो just try to think that how can you sketch the water surface profile, and just remember that when do you know that uh, the flow is supercritical as such. I hope you know that there is one value of depth which is called as critical depth value, in which for every flow scenario there is one value of critical depth value and uniform flow depth value. So these are the two values which you can determine for any discharge value. Okay, using the formula given, like Manning's equation. There are some empirical formulas which are used to determine these values of depth. Okay, uniform flow depth and critical depth value. So you can say that that is a fixed value for constant discharge. Okay, uniform flow depth and critical depth value. Yeah, keeping the slope constant and keeping the cross section constant. Okay, so if you are given with the line of uniform flow depth and critical depth value, then how you can sketch the water surface profile? Just try to use the rules and do that. Whenever the flow changes, like you have to sketch here, whenever there is a control section, there would be gradually varied flow either upstream or downstream. Just remember that. So what would be how the flow would be varying at upstream of the control section. So here in this figure, here is the control section. Now here there is a change in the flow and depth value or relationship, and here is a control section. It is a dam. Okay, and then here also a control section where you can see the change in the slopes. Okay, so are you seeing the cursor moving on the slide?
Yes, ma'am.
Okay, so as the slopes of the channel are changing here, so it is also called as a control section. So it is also called control section. So just remember that every control section is associated with gradually varied flow upstream and downstream of that control section. And how to sketch that water surface profile of that gradually varied flow, you just have to think that. Okay, so in this case you are seeing the control section here. Okay, and the flow is uniform, and when the flow changes from uniform and the uniform flow depth is less than the critical flow depth, it means the flow is called as supercritical flow here. Okay, so if the control section is at downstream of this scenario, like this, it is downstream, control section is downstream. So it means that at the upstream of the control section, the flow depth would be greater than the critical depth value. Okay, so control section is here, so upstream profile would have the greater depth than critical depth. Okay, as this is the point, a downstream control governs if the flow is subcritical. So flow would need to be subcritical if the control is in the downstream. यहाँ पे भी वही हो रहा है. ये control section है, which is downstream of the profile, so it needs to be subcritical. The flow depth should be greater than YC. So if it is greater than YC, so there should be the hydraulic jump in between as subcritical flow, a supercritical flow is changing into subcritical flow. Okay, so this is just a sketch. You don't need to quantify that. What is the distance? What is the distance between the hydraulic jump and the control section? You don't need to calculate that distance, but just sketch it. Try to perceive the scenario and sketch the water surface like this. Then again, here the water surface profile, you can see that it is crossing on the control section. The water surface profile should cross the critical depth line. Now here you can see that for supercritical flow, like in zone 3, this is the supercritical flow, as the value is less than YC in zone 3. So for supercritical flow, the upstream control section governs. Okay, so this S3 is made, and then again the uniform flow depth would be between the two control sections, and then again how to sketch that, you have to think that also further, like similarly you have to think it. Okay, I expect that you'll practice it and ask me any question during the week. If you find there is anything confusing, you can ask me. You can always ask me through an email. My email address is written in the first slide, or you can ask me through the conversation of MS Teams. I'll try to answer your questions. Thank you so much. That's all for today. Please don't forget to do the assignment, which is on this slide.
मैम ये सबमिट कहाँ करनी है आपको? यहीं MS Teams पे इनबॉक्स करनी है?
हाँ, MS Teams पे करते हैं या मुझे ईमेल भी कर सकते हैं आप, लेकिन आप अपना जरा सब्जेक्ट में ये जरूर लिखिए कोर्स का नाम रिवर इंजीनियरिंग और MS 2020. आपका सेशन 2020 है ना, तो सेशन 2020 जरूर लिखिए और रिवर इंजीनियरिंग लिखिए. ठीक है, सब्जेक्ट में आपने ये लिखना है. ईमेल मुझे कर.
ठीक है मैम. मैम इसमें प्रोफाइल्स तो नहीं बनानी है ना, जस्ट कैलकुलेशंस करके बताना है ना कौन सी कर रहा है वो है.
हाँ, क्लासिफिकेशन बतानी है.
ठीक है.
Okay, thank you so much. Let me download your attendance. मैं अभी बाद ये फिर मैं अपलोड कर दूंगी MS Teams पे ये स्लाइड्स. ठीक है, तो आप फिर चेक कर सकते हैं असाइनमेंट. Okay, if there is any question, please let me know. there any question? Okay. Thank you so much, Allah Hafiz.